let's take a look at 9.2 notes. Test about population proportions here. So now we're going to put everything that we talked about in 9.1 together. So we're referring back to your favorite, the 4-step process in doing a test of significance on a population proportion. So here's the steps that you need to follow. So the state, okay? The state, basically what you need to do is you need to state your null hypothesis and your alternative hypothesis using symbol notation, and then you need to define P in the context of the problem, okay? So you write your null hypothesis as P equals, say, 0.5 if we're talking about tossing a coin. The alternative would say it's not a fair coin, we'd say it doesn't equal 0.5. So that's the state. The plan then, in order to do these tests, 3 things must be true, okay? And I will look for 4 things when doing your plan. So the first thing you need to do is identify the type of test you're doing. Just like with confidence intervals, when we say what type of confidence interval we're doing, the plan has to say what type of test we're doing. So we're dealing with one sample. Since we're dealing with a P, we're going to say z-test, and we need to say P, which represents our population proportion. Okay? So the conditions are very similar to that of confidence interval. Is it random? Is it normal? Is it independent? So random, exactly the same. Do we have a simple random sample? Yes, you gotta state it. Normal is almost the same. Instead of saying n times p hat and n times 1 minus p hat, we're now assuming the null hypothesis is true. So whatever this value up here is, that's what you have to put here in your n times p and your n times 1 minus p. Hence why it's p sub 0, proportion of the null hypothesis. The independence piece, the standard deviation, is exactly the same. Okay? If you're sampling without replacement, you need to show that the population is greater than 10 times the sample. So now, how do you actually calculate out your p-value? So this is how it's done. You got to calculate out your test statistic. Okay? So now if we think about our test statistic, okay, it is our p-hat value, it's our sample that we get, minus, okay, the proportion of the null hypothesis, over, and this really should say standard deviation of the null hypothesis. Hence why it's the standard deviation of p times 1 minus p of the null divided by n, take the square root of it. Notice how this is coming from your standard deviation of a sampling distribution, coming right from out of chapter 7. So now, when you get your p-value, you have to make a decision, okay? So if you're doing a greater than test, more than likely your p-value is going to be on the right side. If it's less than, it's going to be on the left side. And if it's a not equal, you have to take into both sets. So when interpreting, I need to see basically 3 things. You need to, 1, interpret the p-value in the context, okay? Then state whether you reject the null hypothesis or fail to reject the null hypothesis by comparing the p-value to your alpha level. And then 3 is you're either going to conclude the alternative in the context of the problem if you reject it, or you fail to conclude the alternative in the context of the problem. Notice how I don't say I actually prove that the null hypothesis is true. I can only conclude that I have evidence that the alternative is true, or I don't have evidence that the alternative is true. All right, so on the next 3 to 4 pages, I'm going to have many examples of this that are already written out, and that's partially to save time. So as you're doing this, you might have to pause the video as I go through these rather quickly. All right, so our first example here goes back to the good old drive-through problem that we were doing with the manager, okay? So, I'm sorry, I'm adjusting this. I'm just going to leave it as such. So, again, going back to the fast food problem, the manager wants to see if he can reduce the proportion by adding another worker, Okay? So if you take a look here, the manager took a simple random sample of 230 customers over the next week, and only 129 of them had to wait at least 2 minutes. Just to let you know, that's your p-hat value. That's your sample proportion that you're going to use in the do to see what the actual p-value is, to see whether or not you have statistical evidence that you actually reduced the proportion of wait times. Okay? So again, our null and alternative hypothesis, this was actually written for us before, but we would say our true proportion is 0.63. We believe our true proportion is getting reduced or is less than 0.63. Again, P is the true proportion of customers who had to wait at least 2 minutes to receive their food, and or receive their food once their order was placed. Okay? So that's the state in blue. All right, the plan is all in red. So yeah, there's a decent amount of work that you have to do here and some writing. So in the plan, what's happening is, it says, first thing we want to state is what type of test we're doing. We're doing a one sample, as you can see, z-test for a proportion. I like to state the level of significance. If it's not given, use 0.05. This one, it wasn't given. So I go through the random, normal, independent. Random, yes, the manager took a simple random sample of 230 customers. Is it normal? So is n times p of the null and n times 1 minus p of the null greater than or equal to 10? Meaning basically, how many customers would we expect to have had to wait at least 2 minutes? Well, we would have had to, or we would have expected at least 144.9, because 230 times 0.63, 144.9, and then 230 minus 0.3, or times 0.37, 1 minus, remember these two numbers add up to 1, hence where that 0.37 is coming from, is 85.1. All right, so since both of these are greater than 10, okay, remember that this is in essence like a binomial situation, n times p, we can use a normal distribution to approximate our probabilities. All right, independent, again, a lot of times this is always the same. We are sampling without replacement. So check, is our population greater than 10 times our sample? 10 times 230, that is 2,300. That is true. So since we are sampling without replacement, we are safe to say that the restaurant has at least 2,300 customers that go through the drive-through in a week. Okay? If you've ever been to a certain McDonald's around, say, the one in Eden Prairie, that one can get very busy, especially during the lunch and dinner rushes. So I think that's definitely probable. All right, so now how do we calculate out Z? So here's our formula, p hat minus the p of the null divided by its standard error, the standard deviation of the null hypothesis. Again, here's p hat right here. So 129 over 230 equals 0.561. So here's kind of what I'm assuming. That's why I like to draw a curve. I assume the null hypothesis is true, so the true proportion is 0.63. I want to know, what's it like to get a sample of 0.561 or less if this is true? So hence I'm going to calculate out my z-score and my p-value. So my z-score, 0.561 minus 0.63 divided by the standard deviation, standard error. If you trust my calculations, plug it into your calculator, you get a z-score of negative 2.17. So p-value, I'm looking for z-scores less than negative 2.17 standard deviations. So I'm 2.1 standard deviations to the left, and I want everything less than that. So if I go normal CDF from negative infinity to negative 2.17, I get a p-value of about 0.015. So the question is, based on this p-value, okay, what's going to be my decision? So in the conclusion, I look for three things. You got to interpret what the p-value means in the context of the problem. Okay? So what does p-value mean? Well, if the null hypothesis was true, okay, meaning if the true proportion of customers had to wait at least 2 minutes was 0.63, then our result, so then our sample proportion of 0.561 or less from a sample of 230 customers would only occur 1.5% of the time. Basically, if the null hypothesis is true, then our result from our sample would only occur that p-value as a percentage of the time. That's the interpretation part. So now, what conclusion are we going to make? So since our p-value is less than alpha, we reject the null hypothesis. Sweet. What does that mean to reject it? Well, that means we have convincing evidence that adding the additional worker would reduce the wait time for the customers. So this manager, based on his little study that he did and his sample, would actually continue to add workers because it's actually he believes it's actually reducing the wait time. Okay? All right, so that's the first problem. Let's keep on looking at more examples. So this one that we just did was a less than problem. So let's take a look at a greater than problem. So on page 2 here it says, on shows like American Idol, which is still running. So this problem is old, but hey, that show is still going on today. Contestants often wonder if there's an advantage to performing last. Seems to make sense. So to investigate this, a random sample of 600 American Idol fans selected to view the audition tapes of 12 never before seen contestants. For each fan, the order of the 12 is randomly determined. Thus, if the order of performance doesn't matter, we would expect 1/12 of the fans to prefer the last contestants they view. So in this study, 59 of 600 fans preferred the last contestant they viewed. Do these data provide convincing evidence that there is an advantage to going last? Okay. So our proportion, this is still another proportion, the proportion that we're looking at is the true proportion of American Idol fans who prefer the last performance. If the order actually doesn't matter, then as stated up here, we would expect 1/12 of the fans to prefer the last contestant. That's the null hypothesis. Okay? The alternative is, well, we think there is an advantage, hence the greater than. So we believe the true proportion is greater than 1/12. Okay? So there's our state. All right, now in red comes our plan. So the 4 things we need: state the test, exactly a repeat of what we just did. We're going to do a 1 sample Z test for a sample proportion at the 5% significance level. We go through random, normal, independent. So yes, we had 600 American Idol fans were randomly selected, and not only that, but I'm going to note that the videos in which they watched were actually randomly determined also. Okay? For normal, I just need to show that n times p and n times 1 minus p are greater than or equal to 10. So 1/12 of 600, I would expect 50 out of the 600 fans to prefer the last contestant, while I would expect 550 out of the 600 to prefer anybody else but the last contestant. Okay? Those are both greater than 10, so normal is good. I am sampling without replacement. So 10 times our population, 10 times 600 is 6,000. I think it's safe to assume there's still at least 6,000 American Idol fans out there. You may want to argue with me about that, but hey, the show is still on TV, so there you go. All right, so now in green is our do. We need to calculate out the p-value so we can determine whether or not we're going to reject or fail to reject our null hypothesis. So again, here's our formula. Our sample proportion was 59 out of 600. So that's 0.0983 as a decimal. Okay. So there's my sample proportion, p hat minus p of the null. 1 divided by 12 as a decimal, 0.0833, divided by the standard deviation. So one of the things I at least did in this problem over here is the normal curve. So we're assuming that it's 1/12. The question is, getting a result this big or bigger, does it give me enough evidence to suggest that there is a statistical advantage of going last? So it is higher. The question is it significantly higher? So when I subtract these two, I get 0.015. My standard error, or my standard deviation here is 0.0113. That gives me a z-score of 1.33. So my p-value is z greater than 1.33, because that's the area I want here. Okay, so this is how you do it on table A. Normal CDF, I would go from 1.33 to infinity. Gives me a p-value of 0.0918. Okay. So basically, in our conclusion now, 3 steps. What does that p-value mean in the context of the problem? So if the null hypothesis is true, so if the true proportion of fans who prefer the last customer is 1/12, then our result, or 1 greater than it, so then our sample proportion of 0.0983 or more from a sample of 600 fans would occur the p-value percentage of the time. So in this case, 9.18% of the time. So now this one, since our p-value is greater than or equal to our significance level of 0.05, we're going to fail to reject the null hypothesis. Again, in this problem, they didn't give us a significance level, so we're going to assume 0.05 unless stated otherwise. So since we failed to reject the null hypothesis, we don't have convincing evidence to conclude there's an advantage to performing last on American Idol. All right, one more example. Because we did a less than and a greater than, I want to show you how to do a not equals to. You're going to see kind of the same process over and over and over again, starting from now through all of chapter 10, the state plan do conclude. Okay? In number 3 here, it says, when the accounting firm of HAL and Associates audits a company's financial records for fraud, they often use a test based on Benford's law. Benford's law states that the distribution of first digits in many real-life sources of data is not uniform. In fact, when there's no fraud, about 30.1% of the numbers in financial records begin with the digit 1. However, if the proportion of digits that are 1 is significantly different from this 0.301 in a random sample of records, HAL and Associates does a much more thorough investigation of the company. So suppose that a random sample of 300 expenses from a company's financial records results in only 68 expenses that begin with the digit 1. So if I think about this, my p hat is going to be 68 out of 300. So that's going to be my sample statistic I'm going to use in step 3. So I'm going to get to that part at the end. So the last question here says, should HAL and Associates do a more thorough investigation of this company? Okay. So again, state plan do conclude. So in blue is our state. P is the true proportion of expenses that begin with the digit 1. Hence why, if we come up here, we say it's equal to 0.301. However, if it's different, significantly different, that could mean too low or too high. Hence why you do the not equals to. Okay? So now, we go to the plan, which is all in red. So again, we're going to do a 1 sample z-test for a population proportion, significance level 5% since it's not stated. So, random. Yes, we have a simple random sample of 30 samples. They selected 30 reports. Okay. Is it normal? Well, if 0.301 or about 30.1% of the 300 started with 1, we would expect 90.3 of them to start with 1, and we would expect 209.7 to start with a digit other than 1. So since both are greater than 10, normal. Independent, we are sampling without replacement. So population greater than 10 times the sample. Is our population at least 3,000? Well, does the company have at least 3,000 expense reports? Well, we need to kind of like assume that this is a relatively big company. So if we start to take a look at companies like Target, General Mills, yeah, they probably have at least 3,000 expenses in their financial records. Okay? So now we want to calculate out the p-value here. So that's everything here in green. So what we do, again, is we're calculating out our z-score. So our p-hat was 68 out of 300, 0.2267. So we're taking that value, minus it from the proportion of the null hypothesis, 0.301, and divided by its standard deviation. So if I think about it picture-wise, I'm assuming that it's supposed to be 0.301. I had this result, okay, that was 0.2267, which is down here on the low side. So my result could be way too low, or it could be equally as far away on the higher side. So what happens is I'll calculate out this lower side and simply double it to get my p-value. So I subtract the top point, or negative 0.0743, standard deviation is 0.0265, divide the two and I get negative 2.80 standard deviations. So what I do is I just do normal CDF of one of the sides. When I do that, as you can see either here or here, I get a p-value or a 0.0026. So that's this area. But technically I could have been above it also. Okay? So I have to double the p-value. So my p-value is 0.0052. So again, as you're kind of getting redundant here, our conclusion has three parts. What does the p-value mean in the context of the problem? So if our null hypothesis is true, if the true proportion of expense reports that begin with the digit 1 was 0.30, then our result, or one more extreme, so our sample proportion of 0.2267 from a sample of 300 or one further away from it. The reason why I say further away, it could have been too low or too high, would only occur 0.52% of the time. So this is happening less than 1% of the time. So again, what are we rejecting or failing to reject? In this case, we would reject it. Since it's less than 5%, p-value is less than 5%, we reject it. What does that mean? Well, that means we have convincing evidence that the proportion of expense reports that begin with the digit 1 is not 0.301. This means AJL and Associates should do a more thorough investigation of this company to check to see if they're actually telling the truth. Whew. All right, so there's just one more, and it's still working with this particular problem. So what's really cool about test of significance is technically you can do confidence intervals to test the claim about the parameter. In order to use a confidence interval, what you do is you just basically check to see whether or not your confidence interval captures the null hypothesis. If the confidence interval captures the null hypothesis, okay, you don't reject because you got it. It's in there. It's what you would expect. However, if your null hypothesis is outside your confidence interval, it gives you actually evidence to reject the null hypothesis. So that's basically summarizing what is being said right here. So to show you how this works, okay, using that same Bedford Law program, or fraud problem, geez, Mr. Parks, you're trying to rush here. So, excuse me, we want to find so to do this, we still do the fund state plan do conclude for a confidence interval going back to chapter 8, okay? So we state what type of interval we're trying to find. So we want to find a 95% confidence interval for the true proportion of expenses that begin with the digit 1 for this company. So what type of interval are we trying to find? A one sample Z interval. So for random, normal, independent, I really didn't repeat random and independent because they're exactly the same as problem 3. Normal does change because remember we have to use p-hat. So it's the actual number of reports we got that started with a 1, and it's the actual number that didn't start with 1, okay? Unlike when doing a test, it's times the null hypothesis. How much would we expect to get? That's a key difference, okay? Sometimes they like to even test you on that on the AP exam. All right, so calculate out that confidence interval. P-hat plus or minus Z star plus times the square root of P-hat, 1 minus P-hat over N. So our P-hat is, again, 0.2267. We calculated that out from before. So Z star, what in the world is going to be Z star? Well, since we're doing a 95% confidence interval, okay, our Z star is going to be 1.960. So now you might be wondering, why 95% confidence interval? Since alpha is 5%, that means we're going to reject 5% of the time. So the area of the tails should be 5%. Hence, the same thing happens in a 95% confidence interval. Not 5% of the scores are outside the interval. All right, so here we go. We calculate it out. Here's our sample proportion plus or minus now the margin of error, and subtract that, and we get our proportion. So we would expect, based off our sample, that the true proportion, okay, would somewhere lie in the interval from 0.1793 to 0.2741. Hence our interpretation of the confidence interval. We're 95% confident that the interval from 0.1793 to 0.2741 captures the true proportion of expenses at this company that begin with the digit 1. Okay? So now if I look at this interval, 0.301 is not in our confidence interval. Okay? So it's not a plausible or a value we would expect for the true proportion. Because of this, we would reject the null hypothesis, meaning this company should be investigated more thoroughly